Okay, guys, it's time to start Chapter 17, Part 2. Going to talk some more about the second messenger system. We talked about, in the previous video, we talked about one type of second messenger. Now we're going to talk about the other type. This one is called the PIP2 calcium signaling mechanism. That PIP has a very long name, and so let's just leave it at PIP2, okay? Now, what happens is this, same as we saw with cyclic AMP on the other one. We have a signaling molecule, which is the first messenger, which is a hormone. Generally, one of the peptides that can't go through the plasma membrane will attach to a receptor that's transmembrane. This receptor, the G protein linked receptor, will cause the G protein with the GTP powering it to go, and that will activate phospholipase C. Phospholipase C will react with the PIP2 molecule. In any case, think of this like a set of dominoes where one causes the next to react, and that's basically what's happening. Now the PIP2 molecule, the phospholipase C is going to split it into two other molecules. It's going to split it into DAG, diacylglycerol, which DAG is fine, and IP3, which is inositol triphosphate, IP3, right? I and then 3 phosphates. IP3 is going to be the second messenger, which is going to go to the endoplasmic reticulum. Basically, it's going to go to the sarcoplasmic reticulum, and it's going to bind to a receptor there, and this receptor is a gated channel. When this IP3 bonds to it, it opens up and lets calcium out, and then the calcium is going to cause some reaction. This happens a lot in muscle tissue. That's where you're going to see this a lot. And that calcium, if you recall back from AMP1, is going to cause the sarcomeres to contract, and in the smooth muscle as well. Okay, continuing on. Really ought to get a pen, I think. If I can. It's not letting me do it. There it is. Sorry guys, it's being real slow about letting me. Okay. Okay, now I got it. Okay, now here we're going to take just a tiny break and we're going to talk about receptors. Now, this is true when you talk about neurotransmitters as well as when you talk about hormonal receptors. If you have very low levels of the hormone, if the hormone levels stay down for a period of time, that will cause these receptors or these cells to actually produce more receptors. Notice that it goes from 2 to 4 to 8. So it's going to increase the number of receptors because there are low levels of hormone, and it's like, they're putting out more so that they can bind whatever is there. They'll have more of a chance to bind it. On the other hand, if you have prolonged high levels of hormone, then you get a decrease in these receptors. Here we see it going from 8 to 4 to 2 because of the high levels, because they're overstimulated. So when you make more receptors, that's upregulation. When you take away what you have, that's downregulation. Okay guys, let's move on to the next page and see what we can find out here. Negative feedback is something you guys have been exposed to in AMP1. We'll go over it again though. So here we got this guy that's eating. That's going to cause his blood sugar levels to skyrocket temporarily as all that glucose floods into the bloodstream. This is going to be detected by the beta cells, in the pancreas. That's going to cause the pancreas to release insulin. Insulin is going to react on, or is going to act on the liver, causing it to take up glucose and making it into glycogen. And it's also going to have an effect on the body cells, causing them to take up more glucose. As these things take it up, then the blood sugar levels drop down. As these levels drop down and the blood sugar levels go back to normal, that's going to be the signal for these guys to stop. So that's the negative feedback. You have high glucose, you release insulin, the glucose goes down. When it goes down, you stop. Pretty straightforward. Most hormones are going to act like this. Positive feedback. And again, this is something we talked about when we were in AMP1, but we'll go over it again. Positive feedback, the most spectacular example of that is going to be labor contractions. So we see the hypothalamus up here in the top corner. You see the pituitary gland underneath it. From the posterior pituitary, we're going to get OT, which is oxytocin. This guy is going to go in the bloodstream because remember he's an endocrine. He's ductless. He's going to make his way to the uterus. The uterus is going to respond to that oxytocin by contracting more. Actually, what happens is that the oxytocin is going to bind on the outside to that G protein, and we're basically going to split PIP2 into IP3 and DAG, and that's going to cause the release of all that extra calcium inside the uterus, which is going to stimulate contractions. Now, I really should have went here first. The thing that stimulated the release of the oxytocin to begin with is stretch receptors around the cervix, around that part of the uterus. As the baby's head moves further into the cervix, it's going to stretch, and that information is going to the hypothalamus, which is going to be the one to cause the release of oxytocin. Now, as this causes this contraction, it's going to actually cause the baby to go even further through the uterus toward the end, and that's going to stimulate yet more. And this cycle is going to continue until the baby is born, in which case the stretch receptors will cease registering any pressure. Okay, how do we get endocrine glands turned on? We got three mechanisms here. We got the humoral, the neural, and the hormonal. Okay, the humoral is when the glands themselves are going to detect an increase or decrease of some sort of chemical, not a hormone, but a chemical. So here's the parathyroid glands on the back of the thyroid. Can't really see those red on red, but anyway. So what's happening is these guys are detecting that there are low levels of calcium in the blood. That's going to stimulate the parathyroid, and it's going to release parathyroid hormone. It's usually abbreviated PTH. So this guy has got humoral stimulation. And by the way, this is negative feedback, obviously. As the blood calcium levels go up, then these guys are going to stop producing the hormone. Okay. So this can work as release or inhibition. Glucagon would be a good example of inhibition. The glucagon raises the blood sugar levels, and when the blood sugar levels get to a certain point, it's going to inhibit the release. Well, even the calcium is going to inhibit. When the calcium levels are high enough, they're going to inhibit the gland. Neural, this guy is basically wired into the nervous system. The sympathetic nervous system will go into the adrenal medulla, this inner part of the adrenal gland, and this is where we have those catecholamines, those guys which are hormone / neurotransmitter. But in any case, the sympathetic nervous system is going to stimulate that guy, causing him to release epinephrine and norepinephrine, fight or flight. And finally, we got the hormone. This is fairly common, in which one endocrine gland is going to turn on and secrete in response to a hormone from another gland. Generally, the gland that's going to be the boss is going to be the pituitary gland, and it's usually the anterior pituitary. These guys are going to make, okay guys, so the pituitary gland at the command of the hypothalamus, the brain. Remember, we said the brain controls all of this. But the pituitary will release a hormone that goes to other glands and causes them. There's something called thyroid stimulating hormone. TSH comes from the pituitary, goes to the thyroid and causes the thyroid to release thyroid hormone. And there are several hormones that go from the pituitary to the cortex of the adrenal. Remember, we talked about the medulla. Well, in the cortex, there's 3 layers, and they have several hormones, more than 3. And then we have one, I think I mentioned this, gonadotropin stimulating hormone, gonadotropin releasing hormone, G, little n, big R, big H. And this goes to the testes or to the ovaries and causes that. Anyway, that's our 3 means of actually turning these guys on. Hormone interactions. Well, these guys, there are 3 ways that these guys can interact. One is synergistic. When the 2 hormones work together, they actually cause a much bigger effect than if they each individually. They could actually oppose each other. One can do the opposite of the other. Now, good example is insulin and glucagon. Insulin lowers blood sugar, glucagon raises blood sugar. And then you have another effect in which one is permissive. One hormone will actually be almost like a gatekeeper, and when that hormone is present, the other hormone will have an effect on the organ. So if the first hormone isn't there, the second hormone can't do its job. Okay, here's the little chart they've got on synergism. This is pretty interesting. Now, glucagon, you notice, is a pretty steep slope there, so it's got a very quick rise, because this is our time in hours. You see it jumps all the way up here to about 40, that's about 110, I would guess. So about 110 going from whatever it was here, probably no more than 70 or 80. But it has a very quick onset, goes up moderately high, and then kind of tapers off over like a 3-hour period of time. And now you have epinephrine over here, the green one. This guy is takes about 3 hours to peak, but he'll come in about, I don't know, a little under, maybe around 120, and then he's going to decrease over a period of a few hours. Down here you have cortisol, this gray one. Cortisol will cause a very tiny increase in blood sugar all by itself. So there's the 3 by themselves. Now let's put them together. If I get glucagon and epinephrine at the same time, then I'm going to have an even faster onset than I do with glucagon by itself. And I'm also going up initially to around, I don't know, that's maybe about 125, 130. And then I'm going to go even higher, maybe to about 150. And I'm going to stay there for a very long period of time. So within 2 hours, I'm going to go up very high. Within minutes, I'm going to reach almost to 150, and then I'm going to complete that. Oh, I'm sorry. Within minutes, I'm going to reach about 125, and then I'm going to eventually, over a couple of hours, hit 150, and I'm going to stay over 140 for hours and hours and hours. But look what happens if I've got glucagon, epinephrine, and cortisol, all 3. the rate of increase is very fast, but I go up higher. I go up to maybe 145, and then it just keeps going up way over 200, which is actually way more than we need. But that's an example of synergism, how these guys working by themselves, they have a mediocre effect, but when they're combined together, they have a much greater effect, way more than just simply adding them would be. Okay, permissiveness. So we have thyroid hormone, which is a gatekeeper. You have the epinephrine. Epinephrine by itself will cause a very small amount of fatty acids released. Thyroid hormone doesn't cause the release of fatty acids, but when the thyroid hormone and the epinephrine both are present at the same time, I get a large amount. So the thyroid hormone is acting as a gatekeeper. He's opening the door so that the epinephrine can have his full effect. And then we've talked about the glucagon and insulin. So in the fed state, which is within an hour or two after dinner, you're going to have a lot of insulin in your body because you've got a lot of blood sugar. You're going to cause the breakdown of glucose. You're going to do a lot of synthesis of glycogen in storage form. You're going to take and make a lot of fat and proteins with that excess glucose. Now after that, and the further you get away from the last time you've eaten, the glucagon is going to predominate. Glycogenolysis means I'm going to take the glycogen and break it down into glucose and release it in the blood. Gluconeogenesis, I'm going to take non-glucose and I'm going to rearrange it to make it glucose. Ketogenesis, I make those ketone bodies which can be burnt as fuel by the body as well. Okay, pituitary gland. You guys hit this in A&P in the brain anatomy. We'll go over it again. There's the pineal gland. We're not really concerned about it right now. Let's focus on the hypothalamus and the pituitary. The hypothalamus is part of the brain. If you remember, there's like 15 different nuclei in there. Nuclei is going to be a collection of cell bodies. Remember, most of the cell bodies in the brain are in that 1/8 of an inch strip of cortex on the outer edge. But if you have cell bodies inside the brain and all that white matter, those are called nuclei or nucleus. There's about 15 of them there, and they do all kinds of different things, and we'll get into some of those here in just a moment. Connecting the hypothalamus to the pituitary is this stalk. It looks like the stem of an apple, and it's called the infundibulum. Now, the pituitary is really not just one big thing. It's actually two very different compartments. You've got the one in the front, the anterior, and you got the one in the back, the posterior. They got this from Junior Dentist. Who would have thought that? Not me, obviously. If you recall, that part of the bone, that's part of the sphenoid bone. It's called that sella turcica, Turkish saddle. That's the area of the skull that the pituitary kind of sits in, and you can see it better up here. Now let's talk about these lobes of the pituitary. You've got a posterior lobe, and basically that's nervous tissue. That is, to be specific, there are nuclei up here with cell bodies, and then they have these long axons, and then their axon terminals. That is what the posterior is. It's really just an extended portion of the brain. On the other hand, the anterior lobe is composed of glandular tissue. Again, if you recall from A&P1, that means mostly epithelial. Now, let's go ahead and use some more terminology. Pituitary gland is oftentimes called the hypophysis. That's its alternate name. So the posterior that has all the neurotissue is called sometimes the neurohypophysis. The anterior lobe, which has the glandular tissue, is called the adenohypophysis. This is good drawing, but I got a way better one on the other side. As a matter of fact, I'm going to jump over there and we'll come back to this. So here we are. Here are those nuclei that I talked about. There's the cell bodies, and there's the long axons. Now, those axons, these nuclei up here actually make hormones. Those neurons make hormones. They make two different hormones. One of them is oxytocin. We talked about that just a few minutes ago, oxytocin. The other is something called antidiuretic hormone, ADH. These two guys are made by the hypothalamus, and they're only stored here. So the posterior gland, posterior portion of the pituitary gland is basically a warehouse. You do not make hormones there, you merely store them. And if you look up there, you can see all the steps, but I've basically went over those. Now let's go back. That is a much better picture than this one, although this one's not bad. Now, here's what we want to talk about over here. We've got two nuclei. I mean, there's more than that there, but we're only concerned with two, with the posterior. There's the paraventricular and the supraoptic nuclei. Okay, the paraventricular nuclei, these guys right here, are going to make oxytocin. The supraoptic is going to make ADH. Okay, so they make them, they go down to the end of the axon terminal, and then how do they get released? These guys fire an action potential just like any other. So these hormones are almost in the same, one of those kind of, almost like neurotransmitter, because it's released the same way. Okay. Oxytocin, we're going to talk about two things. We talked about this, about how the oxytocin is going to cause the smooth muscle of the uterus to contract to push the baby out. Now, there's also another job that oxytocin does. This one is often confused, so let me tell you about another hormone. It's called prolactin. Prolactin is not made in the posterior, okay? It has nothing to do. Prolactin is what causes a mother, after she's had her baby, to produce milk to feed the baby through breastfeeding, okay? Prolactin causes milk to be produced. Oxytocin, remember, it acts on muscles. There's myoepithelial tissue. I know we hadn't got that far yet, but there's myoepithelial tissue in the breast. The oxytocin causes these guys to contract and causes the milk to be pushed out. That's how the milk is actually ejected from the breast to the baby's mouth. Now, the way that we get this is actually the baby, when he starts suckling on the breast, that is going to cause the release of oxytocin, as well as psychological factors from the mom. And again, positive feedback. As long as the baby is suckling, the longer the oxytocin will be released and the more milk will be ejected. So it's also a positive feedback mechanism. Antidiuretic hormone. We're going to talk about this in great detail when it comes to the kidneys, but let's talk about it just briefly. We make a lot of waste materials, toxic waste materials that we have to get out of our bodies, like urea and ammonia, amongst other things. We flush those out of our bodies dissolved in water, and we call that water and waste materials urine. Well, how much water do you use to flush it out? It depends on how dehydrated you are. That's what it depends on. If you drink water all day long, like most of us do, you're going to make very dilute urine. You're going to waste water flushing it out because you got more water than you need. If you're dehydrated, say you've got diarrhea or been throwing up or whatever reason, then this dehydration is going to be detected by the hypothalamus. Now, There's another way it can be detected too, and I'll tell you about that as well. We have osmoreceptors. What those guys do is they monitor the concentration of solutes in the blood. Normally, our blood is like 300 milliosmoles. If it goes up, it usually doesn't mean that we've taken in more salt. It usually means that we have lost water, and that's caused the concentration to go up. So if you had a glass with 1 teaspoon of salt in it, and half the glass of water evaporated, you still have the same amount of salt, but you have half the water. If you have half the water and the same salt, then it's twice as concentrated. So that's what's happening here. When we lose water but not salt, then the concentration goes up. That's monitored by the hypothalamus, and it's going to do several things. It's going to make you say, I'm thirsty, but it's also going to cause the kidneys to use the least amount of water it possibly can to flush out those metabolic waste. And this is going to be second messenger, and it's going to be our cyclic AMP that we talked about. We'll talk about that in much more detail when we get to the renal section. Now, in addition to the osmoreceptors, we also have pressure receptors. The baroreceptors, you got some in the carotid, they're in the arch of the aorta. They monitor blood pressure. If your water volume goes low, then you don't have as much water or fluid in your blood, so you have less pressure. Both of these are going to they're going to be monitored by the hypothalamus. The hypothalamus is going to cause the release of the ADH. The last slide we're going to talk about is what can go wrong with this. What if I have no ADH? What if I don't make it? What's going to happen? Then what's going to happen is no matter how dehydrated I am, I'm going to waste a large amount of water flushing out, up to 20 liters a day. Think about 10 of those Coca-Cola, that's a bad picture of a Coke bottle, 10 of those full of urine per day per person. That's a lot, guys. Of course, people are going to be thirsty. We're not going through all the signs and symptoms, but this is part of what's going on. Now, this can happen in two places. You could have some sort of injury to the head, a tumor involving the pituitary, or for some reason the pituitary is just not working, specifically the posterior pituitary. Then you're not going to make any ADH and there's none available. You can also have damage to the kidney in which the pituitary is making or releasing all the ADH, but these guys don't have the cells and the receptors and they just don't respond to it. So that's called nephrogenic diabetes insipidus. That's the name of what we're talking about, guys. I thought diabetes had to do with blood sugar. Diabetes mellitus does. Diabetes insipidus is all about ADH being absent or ineffective. You're going to extreme thirst, large urine output. You're going to be wasting water. That's a problem, but it gets really serious if the person's thirst center isn't operating, and this happens like when a patient is unconscious or comatose, accident victims who have head trauma, because we don't know that this could be a problem. We're going to monitor everybody's urine output and the amount of fluid they have going in, and we can do IV hydration with IV fluids. All right, guys, that's it for part 2.